Exactly. A wave transfers energy from one point to another without permanently displacing the particles of the medium through which it travels. The particles might move temporarily as the wave passes through, but they return to their original position after the wave has passed.
So you could say that a wave is a string and it gains potential energy and then loses it, and the final effect is a transference of energy without the particles having any displacement.
That's a great analogy. A wave does have similarities to a string in that it can carry potential energy as it moves. In a wave, energy is transferred through the vibration or oscillation of particles in the medium. These particles move back and forth or up and down around their equilibrium positions, but they don't travel with the wave. So, the energy moves through the medium, but the particles themselves don't undergo any net displacement. Sure, a transverse wave is a type of wave where the particle displacement is perpendicular to the direction of wave propagation. Imagine a rope being shaken up and down. The wave travels horizontally along the rope, but the individual points on the rope move up and down. Light is an example of a transverse wave because it consists of oscillating electric and magnetic fields that are perpendicular to the direction the light wave is traveling. These fields oscillate at right angles to each other and to the direction of wave propagation, which is a hallmark of transverse waves.
So, when the Nobel Peace Prize proved that when you observe something, the wave particle function collapses, how can we relate this to things that we don't see versus things that we don't see? When we see things, does a transverse light wave turn into a particle?
The concept you're referring to is related to quantum mechanics, particularly the wave particle duality of light and other quantum particles. In quantum mechanics, particles like photons, light particles, exhibit both wave like and particle like properties. The wave function in quantum mechanics describes the probability distribution of a particle's properties, such as position. When a measurement is made, this wave function collapses to a specific value, and the particle behaves more like a particle than a wave. However, the Nobel Prize wasn't awarded for proving wave function collapse through observation. Instead, it recognized various contributions to our understanding of quantum mechanics. When we observe things in everyday life, we're not typically causing wave function collapse in the quantum sense. Light as a transverse wave doesn't turn into a particle when we see it. Instead, light exhibits both wave-like and particle-like behavior simultaneously, depending on how it's being observed or measured. This duality is a fundamental aspect of quantum physics.
So, if I'm observing a cup, what does that mean for the properties of observation of light in terms of if it's a particle or a wave versus if nobody was observing the cup?
When you're observing a cup, the light reflecting off the cup and entering your eyes is being detected by your visual system, allowing you to perceive the cup. The light itself is always exhibiting both wave-like and particle-like properties. But in everyday situations like looking at a cup, we don't notice this duality. The light behaves in a way that aligns more with our classical understanding of waves, enabling us to see objects. If nobody is observing the cup, the light still reflects off the cup and travels through space. The behavior of the light doesn't fundamentally change based on observation in this everyday scenario. The wave-particle duality of light becomes more apparent in experiments at the quantum level, such as the double-slit experiment, where
But I
observation...
thought that was there not something about local observation in the Nobel Award?
The Nobel Prize in Physics has been awarded for work related to the foundations of quantum mechanics, including aspects of quantum entanglement and non-locality. For example, the 2022 Nobel Prize in Physics was awarded for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. These experiments demonstrated that particles that are entangled affect each other's states instantaneously, even when separated by large distances. This challenges classical notions of locality, where objects are only directly influenced by their immediate surroundings. However, this doesn't mean that everyday observations, like looking at a cup, cause a wave function collapse in the sense discussed in quantum mechanics. The effects observed in quantum experiments don't translate directly to our macroscopic experience of reality, such as observing a cup with our eyes. In the case of looking at a cup, the light behaves in ways consistent with classical physics, allowing us to see the cup without invoking quantum wave function collapse.
So at what point? At what point from going to large to the quantum state, at what point does that start to take effect?
The transition from classical to quantum behavior isn't defined by a specific point, but is more of a gradual shift that depends on various factors, such as the size of the system, temperature, and the scale at which you're observing. In general, quantum effects become significant at very small scales, typically at the atomic or subatomic level. For larger macroscopic objects, like a cup, classical physics does an excellent job of describing their behavior. But as you examine smaller and smaller scales, quantum effects start to emerge. For example, the behavior of electrons in an atom or the properties of photons in certain experiments can only be accurately described using quantum mechanics. So, while there
Okay,
isn't
so would it be a fair thing to say that, okay, so are you saying that, so people, humans who observe light, it like not a cup, just like light and shadows, the property of light, whatever, light coming in a window, whatever. Would it be fair to like maybe assume that different people see light differently because human is the observer and light would be the thing that is being observed, which is the wave?
It's an interesting thought. While the fundamental properties of light are the same for everyone, the perception of light can vary from person to person. This difference in perception is due to how our eyes and brains process visual information, including factors like color vision, brightness sensitivity, and even individual differences in the structure of our eyes. For example, some people might perceive colors slightly differently due to variations in the cones in their retinas, or they might have different sensitivity to light levels. However, the basic
Wait.
physics.
Hypothetically, because human eyes can only see a certain part of the light spectrum, would it be possible in the future for maybe people to get eye implants that can see more of the color spectrum like other animals can?
Yes, hypothetically, it could be possible. Our eyes naturally detect a limited range of the electromagnetic spectrum, primarily visible light. However, with advances in technology and medical science, it's conceivable that future eye implants or prosthetics could extend this range. Researchers are already exploring technologies like retinal implants and bionic eyes to restore vision to those with certain types of blindness.